In this video, we're going to take a look at a Leetcode problem called unique path number 2. So this question is very similar to unique path number 1. I think if you get that question, you probably should be able to understand how to solve this problem. So same thing here. So the robot locates at the top left and everything looks fine. But the thing is that we're given an obstacle, right? In this case, you can see we're given an obstacle. We want to find total unique path for if we're starting at the top left, right? So in this case, you can see that an obstacle and space is marked as 1 and 0 respectively. So if I have an obstacle, that means it's 1, right? There's a 1 there. And that means that for this position to reach the bottom right is going to be 0, right? There's going to be 0 path to reach the bottom right. So you can see here for this, in this case, for this example, there are two ways. You can do it this way, or you can go to down, down, right, right? So there's only two paths because there's an obstacle. So how can we solve this problem? Well, in this case, same thing, just like how we did it in unique path number 1. For each and every single cell, we have to go to the right to figure out how many unique paths if we go to the right, plus the total unique path if we go down, right? So you can see here that if there is a obstacle, if the current cell is 1, then we can just return 0 because there's no unique path to reach the bottom right if there's an obstacle, right? And then same thing on the right, same thing for the current cell, right? In this case, we're starting at the top left. And if there's a situation where the top left or the current cell there's an obstacle, and same thing, there's 0 ways that we can reach the bottom right either. So let's just jump straight into the code. And if you're confused, I highly recommend to check out the unique path number 1 before checking out this video. So basically the idea is that we're just going to have a integer array set as a global variable. So we're going to have grid. Let's just call it grid. So this dot grid is equal to obstacle grid. So what we're going to do is we're going to have a helper function, and we're going to start at 0, right? So basically for this function, what it does, it will return the total unique path for this given coordinate, right? So in this case, we're going to have a method called helper, which takes a row, the current row that we're on, and the current column that we're on. So then what we're going to do is we first check to see if the current coordinate is out of bound, right? So just like the unique path number 1, we can either go to right or go down. So what we have to do is we check to see if row is actually bigger than or equal to grid.length, or if column, right, is actually bigger than or equal to grid at 0.length. If that's the case, then we can just return 0 because they're total. If we're out of bound, then pretty much there's no way that we can go to the bottom right, right? So then what we're going to do is we're going to see if the current element is actually in this case, is a obstacle, right? If it's an obstacle, then we can just return 0 as well. So if grid at row at column is equal to 1, then we can just return 0 because this is the obstacle. There is no way that we can reach the bottom right. Okay, so now we know that the code that we're gonna write now is gonna be very similar to unique path number 1. So basically, the idea is that we're gonna go down, right? So if I go down for total unique path, if I go down, it's gonna be row plus 1, and the column is gonna be the same. And then if I go to the right, in this case, it's going to be row, and the column is going to be column plus 1. And then what we're going to do is we're going to return total unique ways, right? Total unique ways if I go down, plus total unique ways if I go to the right. And this will give us total unique ways to go to the bottom right for this current position. One thing that I forgot to do is if the current position, right, is equal to the last element, right? In this case, the grid or the bottom right, then we can just return 1 because we found one way, right? So if grid at row, or I should say if row is equal to grid.length minus 1 and column is equal to grid at 0.length minus 1, then we can just return 1 because we found one way. Now if we were to run our code, you can see we have our success. So you might be asking like, okay, what if the last position in the 2D array or the grid is a obstacle? Like if this element is a 1, like can we still go there? In this case, we can't because there's an obstacle, then there's 0 way to reach the bottom right, right? So what we can do here is that's why what we did here is like we first check to see if the current position is a 1. If it's 1, we can just return 0 because there's 0 way to return to the bottom right, right? And then we check to see if the current position is a bottom right position, right? So basically what I'm trying to say is that if the last element in the grid is a obstacle, then that means that there's no way that we can be able to reach there, right? So if I were to set this 0 to a 1, you can see we still have succeed. Okay, so what we can do here is we can check to see if the starting point and the end point is 1, right? If it is a 1, then we can just return 0 because there's no way that we can reach the bottom right. So what we can say is this: we can say if grid at 0, right, is equal to a 1, or if a grid at integer m is equal to grid dot length and n is equal to grid at 0 dot length. So if grid at m at n is equal to 1 as well, we can just return 0 because there's no way that we can reach there, right? So now if we were to run, you can see, okay, well, let's see, it's going to be m minus 1 and n minus 1, sorry. So if we were to run the code, you can see we have our success. But this will give us a time complexity of exponential, so we're going to use a 2D cache array to store the pre-computed value. So what we're going to do is that if this condition didn't really satisfy, we're going to define cache is equal to new integer with the size of m times n. So what we're going to do is that if this position is already being pre-computed before, so if cache at row at column does not equal to null, we can just return cache at row at column. And then same thing here, what we're going to do is that we're going to cache this and save this data onto our cache, right? So cache at row is equal to this. And we're just going to return at cache row at column, okay? So this will basically bring the time complexity from exponential to a m times n, where n is number of rows we have and n is number of columns that we have. So now let's try to submit our code, and you can see we have our success. And now let's take a look at how we can be able to do this using a bottom-up approach. So to solve this problem using a bottom-up approach, basically what we're going to do is that we're going to have each and every single cell computed based on the bottom cell, right, and the right cell, right? Just like how we did it in the unique path number 1, the bottom-up approach. For each and every single cell, if we want to know the total unique path for this position to reach the bottom right, in this case is just going to be 1, because in this case this current position is going to be a bottom right position, and we're just going to return 1, where we're going to set the cell to be 1 because there's only one path. And if I'm here, then in this case there's total of 1, right? Because in this case we only have one unique path to go to the bottom right. In this case, just go down, right? If we go to right, and then there's out of bounds, so we can't have that. And if we have an obstacle, if the current cell is an obstacle, then what we're going to do is we're going to set the current cell, right? The total unique path for a current cell to reach the bottom right is just going to be 0, because there's no way that we can reach the bottom right. So we're going to do that, right? And that's the main difference between this problem and the other problem, the unique problem path number 1, is that we have an obstacle. And if we have an obstacle, we can just set it to 0. If it's not an obstacle, we can just basically compute it based on the bottom cell, right? Based on the bottom cell plus the right cell that was pre-computed before. Okay, so now let's take a look at how we can do this in code. So first, I'm gonna rename this, right? We're gonna use a grid instead of an obstacle grid. So is equal to obstacle grid, okay? So then what we're going to do is we're going to have our m, which is equal to grid.length. And we also have n, which is equal to grid at 0.length. Now, in this case, we're going to create our cache array. And the catch here is we're going to have a cache array with the size of m plus 1 and n plus 1. And the reason why we have m plus 1 and n plus 1 is kind of like a temporary row and temporary column that we're probably never going to use. I mean, we're not going to like override it, but we're just going to use it to compute the last row and the last column in our current grid. It's kind of like this, where we have a temporary cache array with an extra column and extra row, and then to compute this value, we're just gonna, check the right and check the bottom, right? In this case, the bottom has a 0. By default, every single element in the cache is 0. So in this case, this is a 0, this is a 0. So the total unique path to reach it here is just gonna be 0 plus 1, because in this case, this is the last element in the grid, so we're just gonna set it to 1. But if it's here, we're just gonna look at the right, look at the bottom. Here, this is 1 and this is 0. 1 plus 0, in this case, we have one unique path to reach the bottom right. And if this is the obstacle, then right away we're gonna set it to 0, right? So this is what we're gonna do, is we're gonna have an I pointer, which is start at m plus 1, m minus 1. The reason why we do m minus 1 here is because if you notice, we're going to have an extra column and extra row. So where do we start? In this case, we're starting at the second last column and second last row, right? So in this case, we're going to have I is equal to m minus 1. And for each and every single iteration, while I is bigger than or equal to 0, I minus minus, right? We're also going to have our inner for loop, which is j is starting at n minus 1. And while j is bigger than or equal to 0 as well, so j minus minus. Okay, so what we're going to do is that for each and every single iteration, first, what we're going to do is we're going to check to see if the current position is a 1, right? If it's an obstacle, then what we're going to do is we're going to just going to or I should say continue, because by default, the integer 2D array cache array is going to be 0. So what we're going to do is for grid at I at j, right? If grid at I at j is equal to 1, then we can just continue, right? Because we know that, okay, at this current position is a obstacle, right? And then what we're going to do is that if the current position, right, if I is equal to m minus 1 and j is equal to n minus 1, right, we're at the the bottom element, then we can just set this position in cache at I at j to be 1, because we know there's one path to reach the bottom right, which is the current cell. Otherwise, if it's not the bottom right, what we're going to do is we're going to say cache at I at j, right, is equal to the total unique path for the bottom cell and total unique path for the right cell, right? So bottom is equal to cache at I plus 1 and j, right? And we also have the right, which is equal to cache at I at j plus 1. So this will give us the right, the total unique path for the right. So for this current position, is going to be bottom plus the right will give us the total unique path for the current cell, right? And at the end, we're just going to return the cache at 0, okay, at 0. So the top element right here, so we want to know the total unique path for this position, right? So the top left. So if we were to run our code, you can see we have our success, right? So if we were to submit, you can see we have our success. And this will give us a time complexity of m times n and space complexity of m times n as well.